Hey everyone, welcome back to my channel. This is part 6 of the series tutorial. So today we are going to convert our side wind speed into wind pressure. So in the last tutorial, we've got our original wind speed and side wind speed. So today we are going to convert our side wind speed into wind pressure. So to get this value though, we are going to use this formula in the code. There's a formula to convert the side wind speed into wind pressure. We've got this formula. P is equals to 0.5 multiplied by the density of air times the side wind speed squared, which is the value that we got in here in our last tutorial. Here. Design wind speed for susceptibility limit states, which is 39 meters per second, and design wind speed for ultimate limit state, which is 57 meters per second. So go to the code, we'll see that the speed design is squared multiplied by Cfic times C time. So P is equals to design wind pressure in pascals, and this PA stands for density of air, which is given as 1.2 kilogram per meter cube. So we're going to convert this kilogram into gram because the unit here of pressure is in pascal. So this gives us a value of 0.0012 gram per cubic meter, and the velocity, side wind speed, which is in meters per second, which is the value that I've already got, and Cfic, which is aerodynamic shift factor, given in the section 5 of this course, which is we are going to cover in the next few minutes, and C time, which is dynamic response factor, as given in the section 6. The value is 1 except where the structure is dynamically wind sensitive. So go back to our structure. This is a bottle frame, and the structure does not comply with the wind sensitive type of structure. So except when we are building a guymass tower or a crane, that is, we talk about very slender elements that is rising high, and it is very sensitive to the dynamic response of the wind. So in this case, we are going to get a value as 1 in here. Alright, so go to section 5 to get the value for aerodynamic shift factor of the same clause, section 5, where you have to get the value of Cpe and Cpi, which is the internal coefficient and the external coefficient for the wall as well as for the roof. So here it is the aerodynamic shift factor shall be determined for the specific surface part of the following. So for enclosed buildings, and we have circular beams, no freestanding wall, no exposed structural member frames and such as lattice tower, no flags and circular shapes, no. I'm going for enclosed building. So because the structure is enclosed by wall and window, so this is an example of an enclosed building. So Cfic I, which is internal pressure, is equals to Cpi times Kci, and for the external pressure, which is Cpe times Ka times Kce times Kl times Kp, and for the frictional drag force, which is Cf times Ka times Kc for frictional drag forces. So these are the coefficients that we're going to add with the formula. So we're going to multiply with the formula in here times the C time, which is already 1, to get the pressure, maximum wind pressure for windward, sideward, leeward, and also for the roofing. So I've put everything on the Microsoft Word. So what I'm going to do now is I'm going to show you step by step the value and the explanation how we get those values from the code. So if you see here, from the code we get this 4 direction, which is the wind orthogonal direction, which is 0 from here and 90 degrees from here to the right, and 180 to the bottom, and 270 degrees from the left. So my building will be oriented are shown in this particular figure, which is here. Go to my plan view. This will be my 0, this will be my 90 this side, and then this side at the bottom will be my 180, and on my left side will be my 270 degrees. So take note of this and go back to the formula that we have seen in the code. Wind design pressure is equals to 0.5 times the density times velocity, which is these two values, squared times Cp times C dynamic. So initially what I've got is I've got these values at every angle. When the wind is coming, it is 0 degrees, at 90 degrees, at 180 degrees, and at 270 degrees. I've got these initial values times Cfic times C dynamics. So for sensibility limit states, for every angle at 0, 90 degrees, 180 degrees, and 270 degrees, I came with a value which is 0.9 kPa times, which is a constant value, times Cfic times C dynamics. Cfic's value we are going to find, which is in the next few minutes in here below. Same thing for the ultimate pressure, which is 1.97 times, which is the constant value, multiplied by Cfic times C dynamics. C dynamics is 1. So if you go to your calculator, so to prove it, how to get this value, let me open my calculator here. Okay, so for example here, at 0 degree, so it is 0.5 on a calculator, times the density of air, which is 1.2 kilograms. We are going to convert it into gram, times 0.0012, and then multiply by the sensibility limit state for the wind speed, which is 39 meters per second. So 39.01 times, which is squared, 39.01 equal 0.91. So 0.91, which is a constant value, constant value, but I have not found the Cfic and sin time. So we are going to find those values later on. As soon as we find these values later on, then we multiply back by this constant, which is 0.91, to get the actual net wind pressure. Same thing for the ultimate limit states, 0.5 times the air density times the side wind speed, which is squared. Here in this case we have 57.27 meters per second squared, and then we'll get a value as constant value as 1.97 times Cfic times C times kPa. So move on. So the next thing that we need to get is to get our Cfic. So to get our Cfic, go to the section 5. Remember the clause says go to section 5. And here, go to section 5. So go to section 5 of the same book, where we are going to get our external pressure and internal pressure. So the first thing that we need to get is to get our external pressure we get our internal pressure. So go to clause 5.2.1, open the same manual, 5.2.1, there we go. Go back to the here. For my external pressure, Cp is equals to Ka times Kce times Ki times Kp, and then internal pressure, which is Cpi times Kci. Okay, so to get the coefficient for external pressure, we need to get the building dimension, which is, remember, in my previous video, I've given Z value which is given as 6.181. So I've rounded this value as 6.2. H stands for the average roof height or the average height of the structure, which is 6.2. So A, which is my long direction, which is 50 meter, and B, which is my width, which is 20 meter, and the roof slope, which is 10 degrees. If you can see it in here, that's the slope of the roof, which is 10 degrees, and these are the ratios. So if you go to the close, if you go to the code, you see it in here. For one external pressure, CPE, rectangular enclosed building, the ratio of D over P is less than 1. And then roof shape, we have hip or gable roof. This is the wind direction for 0 and 90 degrees. And for the roof pitch, because my roof pitch is actually 10 degrees, so I'm going to go for this column. D over P is less than 1, so my external pressure, that is negative 0.5. Go back. We'll see it later on in the table. So these are the ratios, which is D on B, which is 0.4, which is less than 1. H on D for the roof, which is 0.81, is less than 1. And the ratio of A over B, which is 2.5, and ratio on H on D, which is 0.12. So we're going to see the expansion later on. So for the coefficient, external coefficient, we are going to get the external coefficient for roof, external coefficient for wall, and then for wall for leeward side, windward side, and for side wall and windward. So for the coefficient for the gable roof, for the slope, that is equivalent is equal to 10. If you go to the code, go up here. Okay, roof. For roof external pressure coefficient CPE, rectangular enclosed building, for all values, which is value in this case, my slope is 10 degrees. We have this particular 0 to 5 times h, 0.5 to 1h, 1h to 2h, 2h to 3h, and greater than 3h. What it means is, when the wind, for example, the wind comes to, let me go to my building plan here. Let me consider, let me assume that the windward is this side, on my right side. So for the roof external pressure, 0 to 5h, it means the distance from here to here, and then 0.5 to, what's the next distance? 0.5 to 1h, then 1h to 2h. If my windward is this side, so 0 to 0.5h will be this distance, then 0.5 to 1h will be this particular distance, 1h to 2h will be this side, same as this side. If my windward in this side, therefore my 0 to 0.5 1h will be this side, then 0.5 to 1h so will be this side, as well as in this side. So that's what it means from this table. As you can see in here, here. So these are my CPE value. In this case, we have only two cases for CPE value, because in the code it gives us two values, which is 0.9 and 0.4. For 0.5 to 1h, which is 0.9 to 0.4. 1h to 2h is 0.5 and 0. It's quite easy. It's not tricky. All you need to do is see the code and the building dimension, the slope, and then comply everything with the code, with the data that's given in the code book. So greater than 3h, my CPE for the roof, which is negative 0.2 and 0.2. Here, which is in here, negative 0.2 and 0.2. That's for the wind at 90 degrees, and I'm assuming that my wind is coming in this direction. So for the next CPE value, which is, we are going to change the wind direction, which is from this direction, which is 0 and 180 degrees. So my CPE value I've gotten from the code, negative 0.75 and negative 0.32. Negative because the wind, it is away from the surface. If it is positive, it is towards the surface. So go back to the code. Go back to the code here. Here it is. Negative. Let me show you. This is the negative. It means away from the surface. If it is positive, it is towards the surface. Let me show you. Here. Yeah. When you see a negative sign, it means it is away from the surface. When a positive sign, it means it goes towards the surface. So go back to the CPE for roof. Here. For upwind, we've got negative 0.75 and negative 0.32 at 0 and 180 degrees. So roof upwind, here it is, at slope 10 degrees. For the ratio h over d, which is less than, go back, remember what we have seen in the previous line here, h on d. Okay, my degree is 0 and 180, h on d, which is 0.31. So 0.31, go to the code, h on d, which is less than between 0.25 and 0.5. And my roof pitch is 10 degrees. So what I'm going to do is interpolate these values. I'm going to interpolate this value and interpolate this value to get my CPE at the upwind at 10 degrees slope. So that's why I get this value, that is negative 0.75, because this interpolated value between 0.7 and 0.9, and the next one is between 0.3 and 0.4. Got it in here. Negative, by the way, because it is away from the surface. And the CPE value for the downwind, which is negative 0.35. This stands for downwind. If you go to the code, you will see, I'll show you somewhere here. Okay. Here. So U stands for upwind, R stands for crosswind, D stands for downwind. Then wind, W stands for windward, S stands for sideward, and L stands for leeward. So these are the terms that you should be familiar by now. So go back to the roof. For the downwind, that's for D. Roof slope at 10 degrees, H on D, which is between, remember my ratio is between 0.25, and this is my ratio 0.21. So what I've got this value is just interpolate this value 0.3 and -0.5, which I got this value from here, negative 0.35. So after I've gotten all the Cpe value, now the next thing is plug those values back to the formula, which is in here, to get our wind pressure, which is the next table. So pressure for cable roof, which is I've got two values, which is I've highlighted in blue and green. Blue stands for the submersibility limit state for wind pressure, and the green stands for the ultimate limit states for wind pressure. So as you can see, initially we've got two values for Cpe. We have negative 0.90 and negative 0.4. In these two scenarios, what the code says is that you are going to get maximum value when after you have you've got your net pressure. So in this case, I've got two values, which is negative 0.82 and negative 0.37. So the maximum value is negative 0.82, which is the net pressure for the submersibility limit states at 0 to 0.5 H. Then for 0.5 to 1 H, the maximum value will be negative 0.82. At 1 H to 2 H, the value will be negative 0.46. As you can see, as the distance increases from the face of the wind wall, you can see that the net pressure decreases. It starts from negative 0.82 to negative 0.39. And it makes sense. Same too with the ultimate wind pressure. This is the face of the windward wall, which is negative 1.77. Then at the end of the face of the windward wall is negative 39, which is the wind reduces as it goes further from the windward side of the structure. So the same thing in here as for the upwind roof. I've got my maximum value for the one thing I forgot. As you can see, the small s stands for serviceability and the u stands for ultimate limit states, which is I've gotten the value from the here. I've got to multiply this value by this value to get the value of negative 0.82. It's very simple. You get the value of this ultimate limit state, which is 1.97, and then you got to multiply by negative 0.90 to get my 1.77. You can try it on a calculator and see. So I've got my roof pressure. So the next thing is, after we've got the roof pressure, you need to get the external pressure for the wall. Remember, when the wind comes, there is suction on the roof also as well on the wall. So you need to get your net pressure on the wall as well as on the roof. So what we've got so far is we've got our net pressure on the roof here. Our net pressure on the roof, which is we are going to apply all this pressure into this rafter. So the next thing that we need to get is we get our net pressure for the wall, so that we can apply the wind pressure on the column. So go back, same thing that we need to go back to the code and get our external pressure for the wall, which is in the let me see, roof external pressure. Okay, we are already done with that. Wall external pressure must be from here. Yeah, wall external pressure for table 5.28 for rectangular wall and closed building, wind wall W. So for H, that is less than 25 meter. For elevated, for H, that is height of the average roof, that is less than 25. For building on the ground, when the wind varies with height, or 0.7 when the wind is taken at height z. So because I have specified my z value, which is equal to z, which is equal to 6.181, I've rounded to 6.2. So I'm going to consider my CPE value for wall, which is 0.7. So 0.7, which is in here. It's very simple. So windward for every direction at 0 degree, at 90 degree, at 80 degrees, sorry, 180 degrees, and at 270 degrees, which is in all the directions. My CPE for wall will be 0.7. All same true. And then I'm going to get my CPE for the leeward side. You see, when the wind comes, let me show you here. Okay, go to the diagram. Okay, let me assume that this is my windward side at 90 degree. So this is my windward side. At 0 degree, this is my side wall, and 0 degree will be my side wall, and at 270 degree will be my leeward side. So this is what it means by here, leeward side. So the coefficient for the CPE for the leeward side, go back to the code. Go back to the code. Okay, wall external pressure for rectangular enclosed, yeah, leeward side here, L. For the wind direction, 0, 90. For gable roof, for my slope is 10 degrees. D over B, my ratio is less than 1, so my wind pressure is negative 0.5, which is the suction wall. So you can see in here, negative 0.5. Yeah, here. Sorry, D over B, my ratio is 2. I've got a value of negative 0.3. Go back to the report here, negative 0.3. D over B, go back to the ratio D over B. For the wall, yeah, D on B, which is 2.5, which is greater than 2. That's why I've got the value as negative 0.3 from the table here. D on B for wall to negative 0.3. Okay, so after we've got the value for CPE, plug this value back with the formula, which is multiply this by this constant, which is 0.91 for self-stability limit states and 1.97 for ultimate limit states, to get the net pressure for windward and leeward side. So in all these scenarios, because there is no two value for CP, we have only one value. That's why we got only one here. In all other cases, we have only, in other cases we have two values, which is we have only two values. Then we have to get the maximum value. But for the CPE for windward and leeward, we have only one value. That's why we get only one value for the net pressure. So for the ultimate limit state, we got here 0.64 kiloton per meter square, and for the windward, for the ultimate limit state, is 1.38 kilonewton per meter square. So the same thing for the side wall. Goes to the side wall. If I'm assuming, okay, go back to my my picture here. So far we've got already the CPE and the wind pressure for windward and the leeward side, but the side wall we have not got it yet. So the side wall, what it says here is that when the wind comes here, this is my windward. This side, which is side is represented by the letter AA. Is going to be divided by 0 to 0.5 times h, 0.5 to 1h, 1h times 2h, 2h to 3h, and greater than 3h. So 0 to 0.5h, and then 0.5 to 1h, then 1h to 2h, 2h to 3h, and then this side at the far end will be greater than 3h. That's what it means by from this table, from here. So to get the Cpe for the leeward side, go back to the table. Here, go down, go up. All external pressure, Cpe for leeward, this for leeward side. Come on, my side wall, yeah, this is my side wall. So 0 to 1h would be negative 0.65, 1h to 2h would be negative 0.5, 2h to 3h will be negative 0.3, and greater than 3h will be 0.2. So this value, I've got these values and then plug it in into here. This is where I get my value from. Hold on, here. Negative 0.65, negative 0.5, negative 0.3, negative 0.2. As you can see also written here on the code. So now that I've gotten this value for the Cpe for the side wall, all I need to do is get all this value for Cpe, multiply by the constant that I've already found here, which is 0.91 for the serviceability limit states and 1.97 for the limit states, to get a value here below. Pressure for windward wall and leeward wall. Here. Pressure for side wall. This is for the serviceability limit states, which is I've highlighted in blue, and the green one for the ultimate limit states. As you can also see, this is from close to the face of the wind wall. We have high value of the wind pressure. As the distance increases from the far away from the windward edge, the net pressure also decreases. It also makes sense. Like I said, if the winds come here, this side will be 0 to 1h, 1h to 2h, and then 2h to 3h, and this side will be greater than the h. So this side will experience less pressure from the windward effect on this side. Okay, so I've got all these values, and what we did so far is we've gotten our Cpe, but we have not got our Cpi, which is here, internal wind pressure. So at the end of the day, the difference between the Cpe and the Cpi value will give you the net pressure on a particular wall or roof. So my Cpi value, because my building it has 2 permeable wall. If you go to the floor plan here, yeah, this side and this side are permeable wall. It means we have windows this side to be open, and that's what I mean. The wall have permeable, and this side it is closed and this side is closed. So we have two side wall that are permeable that are given in the code. If we have two wall sides are permeable, then Cpi at 0 degrees is negative 0.1, and Cpi, another scenario, will be 0.2. Then Cpi at 90 degrees, which is this side, will be negative 0.3. Then another scenario will be 0. So at the end of the day, we are going to get a maximum value for the net pressure for the internal pressure, because we have two values. Like I said, in here, okay, go back to the code. CPI value. So CPI value somewhere here. Anyway, CPI value, internal wall pressure. Yeah. So this is my internal wall pressure. For building with open plan cases for permeable wall without dominant opening. So I'm going to use this table 5.1b down table 5.1b says internal wall pressure coefficient for building with open internal plan dominant opening. No, I don't have dominant opening in my here. There's no dominant opening in here. So I'm going to use the first table, which is table 5.1a. So for windward with permeable wall, for windward with impermeable wall, for windward wall with permeable wall, windward wall with impermeable wall, because I have two sides which is permeable. So in this scenario, I'm going to use this table here. As you can see, I have written down on the Word document there, which is negative 0.1, 0.2, which is the first scenario, negative 0.1 and 0.2. And then for windward wall, impermeable, sorry, for all wall impermeable, negative 0.3 and 0. That's why I've got it from here. So I'll go back. Negative 0.3 and 0. So the same step that we did initially for the CPE value, get all the CPE and multiply it by here CPI times KCI, then multiply by the coefficient that we got here to get the value from the table below. So this is my final value. For each and every scenario, I've got to get the maximum value for the CPI, which is in this case I've got 0.2, which is the maximum value, 0.29 maximum value, 0.20 maximum value, and negative 0.3 and negative 0.59. This is for the serviceability limit states and ultimate limit states. We got it here. Okay, so that's how we get our net pressure for the windward, leeward side, as well as the side wall. So all that we have done so far is we got our external pressure and internal pressure. So at the end of the day, we've got to combine the external pressure and the internal pressure to get the force on a surface. For each and every surface, we have to get the net pressure for the external and the internal pressure in order for you to get the net pressure that on a surface that we're trying to get. Okay, so thank you very much for watching. I'll encourage you to watch the video again. If anything that you don't understand, feel free to comment below, and I'll try my best to get back to you. Alright, thank you very much. In the next video, we are going to get the net pressure, which is the difference between the internal pressure and the external pressure, and then start applying our load back into a structure in macro slab. Thanks for watching. I'll see you in the next video.